Okay, in the previous session we talked about project estimating and we talked about top-down versus bottom-up estimating. First we're going to look at top-down estimating. So there's several methods for doing that. Consensus method, ratio method, apportion method, some methods for software projects and for learning curves. And this learning curves is for production. I'm going to show that this is a top-down, but we'll see when we do learning curves, we really could also use it for bottom-up. But let's go through these methods here and talk about these. So first is consensus. So consensus is, I've had experience in multiple projects in my past, and I've had maybe different programs. I'm going to show you lots of notional data in this section just to give you ideas, but data is not accurate, it's just notional. So maybe I've worked several programs, one for the Navy, for infrared, one for international laser, maybe an Army program, a radar. I've different periods of time, different costs, and man months over here. So usually 165 hours per month. So that's 1,200 man months times 165. That's how many hours worth of effort we've had on the project. Now, based on this, my team and I can get together and say, this new program is kind of like this program here and this there, and we can kind of put it together and say, we think this program, this new program, should be in this range, 350 million or some number depending on the program. So we can now come up with a consensus from the team based on our knowledge from data we have on past programs and our experience of how this program relates, come up with a consensus, and we're going to say now, here's projects A, B, C, and D. Project E will be this many dollars. Nice way of doing this when you have some senior people been through this and you have the data. Most of your companies got tons of data on these past projects that you can bounce this new estimate off of. So that's consensus data. Ratio method, again, notional data. I'm not in the construction business, but I can imagine they would have this types of data. So let's look at this. I now need to estimate 2 miles of roadway, 1 200-foot bridge, and 3 intersections. Okay, I don't even have to go out and look at that job yet. I can come in and say, look, on my previous 3 jobs, it cost me an average of $2.3 million per mile to pave. It cost me $108,000 per foot of bridge. And it costs me $500,000 per intersection. Okay, now I can just take those numbers, 2 miles times 2.3 million per mile, 200 feet of bridge up here times 108K per foot, 3 intersections, going to add 20% profit, so multiply by 1.2. I have a $33 million job, roughly speaking. Now, when my team goes out and looks at it, they might say this job's a little harder or a little easier to pave, this bridge is going to be a little harder or easier. They could refine that estimate. But if they come up much different than 33, based on my good averages from the past, I need a rationale. But at least I've got a rough idea what this job is. And if I know the customer doesn't even have this much money, I may not even spend the time bidding. So it just depends. So ratio method gives you another good way of doing it. Another way of doing this is you and I buy houses, and typically here we say a house is whatever, $300 a square foot a house. So if I want a new house to build and I got 1,000 square feet, I can multiply it times 300 per square foot, and I can know the house is going to roughly cost me this much after I got the land. So a ratio method. Apportion method's a little different. You base this off previous projects that are really closely related. So iPhone 7's based on 6 and 5. I knew my costs for 6 and 5. I can almost allocate the same budget for 7. Yeah, 6 and 5 had new features, 7's got new features, but if we believe we're kind of adding the same amount of new features each time, I can come up with a rough cost based on historical data. And better yet, I can even break it down to, based on past data, how much goes into each phase of the project. And I don't know if this was just notional in the book, but you can come up with phase. For me, remember I had 7 organizations, I'm sorry, 6, I shrunk it down to 6 organizations in engineering. I can look and see, based on previous programs, how much effort is there for systems engineering, integration tests, electrical, mechanical, and so forth. So I can see that integration tests, what's that averaging, about 18%, electrical, and so forth. So now I have a breakdown by program of what that is, and if some of these organizations are much higher on one, I need to understand why. I mean, it's possible. Let's just say I'm redoing a missile and there's no hardware change, but there's a ton of software change. Well, then electrical might be lower and software might be higher. But I now understand it and I can base it off some historicals. Now here's a caution for you. You have a budget and you need to meet this budget. And in order to produce this project, you need electrical, you need mechanical, you need your software. And you need somebody to integrate and test and put it together. But your bid's coming in too high and the boss is saying, cut the bid, cut the bid. What do you typically do? You go in here and you cut system engineering and product support. Now, let me caution you when you do this. Let's look at this data here in the next chart. Let's look at this here. This is, first let's just look at the left-hand side, cost overruns. This is actual cost over what your planned cost is. Okay? Across the bottom is the percentage of system engineering effort. So look at this. Actual cost, planned cost comes in right about 1. In other words, the program costs what you thought it was, as long as you're spending about 16% on system engineering. If you try cutting your system engineering, your actual cost is typically going to come in more than your planned cost. Why? Those systems engineers are defining the requirements up front. If you don't define those requirements adequately and understand the interfaces, requirements, and everything, you have churn in your mechanical and electrical that ends up costing you more money. And this curve on the right is the same data across the bottom, system engineering effort, but now actual schedule over planned schedule. So same thing, you cut your system engineering, what happens? Your schedule falls apart. So caution on cutting your system engineering, even though the first thing it seems like the right thing to do is to cut that. So just a caution on that. Okay, production. So you might have to bid. Those last estimates were really kind of more development programs. But now let's say you have to estimate a production cost. Well, there's 3 pieces. First part's management. That's easy. You need your program manager, maybe you need a factory manager, maybe you need a quality manager, whatever. So you kind of have an idea of what managers you need in there. So you kind of put in some financial person. So you put in some management costs. The next 2 pieces are, let's start at the bottom. You need touch labor, somebody who's touching it and actually assembling the product. You need that cost. Okay, and I'm talking just labor cost here. You obviously have to bid all the material, but you should have a good estimate on the material. I'm talking the labor costs. So we have touch labor, and that's how much hours per putting each one together, and we're going to base that on what's called a learning curve. We'll get into that next. And then you have support costs. What do I mean by that? So you got hundreds of factory workers. Well, they're going to run into problems in the factory. You're going to have obsolescence. They can't get a part. So do you replace this transistor with another transistor or whatever? Suppliers have trouble. So what's going to happen if suppliers have trouble? Or there's a quality issue. So generally speaking, you have to bid some engineering support to help out the touch labor. First, let's look at the touch labor. So we're going to bid touch labor, and again, you have to bid all the material, but you know what your material is. You have to bid your touch labor, and we usually bid this on what's called a learning curve. You and I put together something at home the first time, and reading the instructions and figuring it out takes X hours. You have to put another one together. Let's say you're putting some bookshelves together, whatever. And the second one's going to be a lot easier than the first one. If you had to put together 3 or 4, each one's going to get a little easier and a little quicker. That's called a learning curve. And how's that work? Every time the output doubles, in other words, I go from 1 bookcase to 2 bookcases, I doubled, the second one is going to be some percentage easier. And that's that learning curve percentage. In this example, I'll go through is 80%. Okay? The next double, so I went from 1 bookcase to 2, now let's go to 4. The fourth one is going to be 80% of the second one every time it doubles. So let's look at this example. I said T1, you'll hear the terminology T1, okay, for the first unit, 100 hours. 80% learning curve, that's what your business has experienced in the past, 80%. Second unit, 8.8 times 100, 80 hours. Fourth unit, 80% learning curve, 80 times 8.8 gives me 64. Eighth unit doubles again, you can do the math. Now, this is easy to do the math. There are tables that do this. So instead of 100 hours, it just normalized everything to 1 hour. But look at this. By the 16th unit, I get 0.41. Okay, that's what I had up here. 0.41 times 100, same thing. So the tables will do that for you. There's these learning curve tables. That was big in the older days for me when we didn't have all the calculators and computers. Now you can compute it pretty easy. But let's say you don't have a double unit, 16, 18. So what's 16? The next double is 32. Well, but I want to know what unit 22 is. There's the values there. So the table is nice. And that's based on the learning curve. This is what it looks like here if I graphed it. So if I had a 90% learning curve, 100 hours for that first unit. This is how the labor comes down per unit. 80%, 70, and you can see that. If I graph this on a log, you can see I'd get straight lines on those learning curves. So just different ways of plotting that data. If you're interested in the math, this is the math. We're not going to get that complicated in the course, but just be aware it's out there. So for any unit Y, based on direct hours for the first unit K, okay, and the learning percentage B, you could go calculate that value, so that gives you that table. All right, that's out there if you ever want it. Again, we're not going to get into that detail in the course. Now, cumulative. Before it was unit 1, unit 2, 4, 8. Well, let's say I want to know how many hours I spend cumulative for so many units. Okay? So let's say the first unit was 1, everything is normalized to 1, and if I did 16 units, you would say, well, that's 16. 1 times 16. But, well, wait, I'm learning on each one. Okay, so if I'm learning on each one, how many hours does it really take me to do 16? So again, normalized 1. If it took you 1 hour for the first one, it would take you, going down here for 16, 8.9 hours, so almost 9 hours to do 16 of them. So not 16 hours, not 16 times 1, because you're learning on each one. It's going to take you 9 hours total. So this is what's called the learning curve, and this is cumulative. Cumulative is probably more beneficial to you than the previous, because usually the project you're going to have to bid is tell me how much it is for X number of units. Okay. Again, if you wanted the math, here's the math. Again, we're not going to get into that in detail, but you have the tables or you can do the math. So here's an example. I think this hopefully might put it together for you, because I also threw in material here. So Suboptimum Boat Company produces a mini sub for $500,000, $500,000, $200,000 for material, and $300,000 for labor. We've agreed to 20% profit. We're willing to contract on a 70% learning curve. So we know in our business we can build these mini subs 70% learning curve. Boss comes and says, how much is it going to cost for 4 mini subs? You have to put together that bid. He wants a high-level bid. $500,000 first one. Second one, it's $200,000 material, labor $300,000, but I got a 70% learning curve, 0.7 times that, $210,000 now for labor, so it's $410,000 for the second unit. So the first unit $500, second one's $410. Third unit, materials $300,000. I have to go to the learning curve table now. Third unit's 0.5682, so it's $170,000 or $370 total. Fourth unit, 0.7 times 0.7 is 0.49 because it's doubled. Fourth is doubled of 2, so, or I could have gone to the tables. 147, 347. Now I can add these up. Now look at what it's costing me. Total cost $1.6 million. Not $2 million, because I'm not just taking 500 times 4. I can add my 20% profit. Boss, this should cost with profit. Remember, cost is your cost, selling price. Price is what's priced to the customer. $1.95 million. So that's how you would do this. And if you wanted to say what's the average cost per sub would have been $406. I'm not sure if that matters or not, because you were asked for the total bid. Now, here's a caution. Material, but this will take you more time. Material, let's say you're buying the motors from somebody, that's part of the material. Do they have a learning curve? So yes, the material might have been $200,000 the first time. Could material get cheaper each time because your suppliers have a learning curve? I didn't take that into account here, but in the real world you should. Your suppliers probably also have learning curves. If all this material was pure metal, and that's all you were buying for material, then maybe you don't. But typically in technology projects, we're buying components and things from suppliers, and many times they could have a learning curve also. So you may have to also account for that. So that's the learning curve. Now the last, well, let me talk about this first. So some guidelines. The more hand assembly you have, probably the bigger learning curve you could end up having. If the amount of hand assembly was small on your product, then your learning curve's not going to be really large. So again, each company is going to have a different learning curve estimate. Here was some data I found just on different places, but again, research your company and see what their typical learning curves are. Finally, let's talk about support labor. Remember I talked about problem resolution, obsolescence, supplier, and quality. typically what you do for this, and this is usually fairly easy too, again, your business should have a rough idea of what the support to touch ratio is. So for every hour of labor, you need so much support. And generally speaking, depending on how simple the product is, that could be a pretty low number. So let's say 0.1 means for every 10 factory workers you have, you need one person supporting them. So that would be a support to touch of 0.1. Now, if you're doing a complicated satellite, the support to touch may be 1-to-1. You need an engineer for every technician. So you're going to have differences in your business. If it's really a simple product, that support to touch might be 1-to-50 factory labor. But your business should have that. So now once you know how many total labor hours you had, based on your learning curve and your total labor hours, you can bid your support hours in there. Okay, so now you can bid that. So now you had your management, you had your touch, and you add your support. So that's a top-down approach for doing production. Again, you can see how this could really be used for a bottom-up also, especially if you have really good data existing in the company. So that's top-down. Next we'll go to bottom-up estimate.